So today we will resume our discussion on chemical admixtures. In the last class we saw the basic structures that go into making these molecules. Most of these superplasticizers that we were talking about are water reducing or water soluble polymers, and primarily they have the mechanism of surface adsorption, while the older class of polymers leads to an electrostatic repulsion after surface adsorption. The new class of polymers causes repulsion of the cement particles by steric hindrance. Now, steric hindrance is associated with the bulky side chains that you have in these polymers, because of which they have much superior water reduction properties as opposed to the older generation admixtures. Further, the slump retention is also much better when we have polycarboxylic ether or graph chain copolymers, which are essentially working with the principle of steric hindrance. Okay. So, we were also looking at some comparisons of different types of superplasticizers. We came across a term called modified lignosulfonates. So, lignosulfonates, as you know, are water reducers. If you use them at high dosages, they do act as superplasticizer, but the problem is they can lead to excessive air entrainment and retardation. So, to ensure that these two aspects do not happen, what do we do to modify the structure? We remove the low molecular weight components, which leads to air entrainment, and we remove the sugars from the lignosulfonates by fermentation. Right? Once you remove the sugars, you can modify the structure of the lignosulfonate and make it much more effective as a superplasticizer. The advantage that this gives is now that it can be blended with SNF or PCE admixtures. You can effectively lower the cost of the SNF and PCE admixtures and at the same time provide some degree of retardation to the concrete to ensure that you are able to complete your concreting processes well in time. Okay. So, those are the aspects that we were talking about in terms of comparison of properties and performance of different types of superplasticizers. Now, cost is something which is obviously uppermost in the minds of all project managers. They want to look at how the incorporation of new ingredients can change the costs of the concrete. One thing we ought to remember that the cost is often related to the initial cost that we have for the raw materials that are used for preparation of the concrete. The cost truly does not take into account the improvement in the concreting processes when you have a superplasticizer that is added to the concrete. Work becomes all that more easier with superplasticizers because you are now working with a higher workability, as a result of which you are actually obtaining your concrete at lower total cost. If you consider the time taken for construction, consider the time taken or energy spent in actually vibrating the concrete and so on and so forth. Right. So, if you take that cost into account, the overall cost that you always get with superplasticizers will be definitely beneficial or lesser as compared to the cost without superplasticizers. And again, we have also discussed the fact that to produce concrete with low cementitious contents, it is always better to have superplasticizers in the blend to ensure that you are able to get workability at the lower water contents that are typically used. So, without superplasticizers, you will be ending up spending much more on the quantity of cement that you add to the concrete mixture, right. Nevertheless, if you look at the costs of the superplasticizing molecules that are available in the market today, what is presented here is the relative cost between acrylic polymer, melamine, naphthalene formaldehyde and modified lignosulfonate. So, the cost of the dry polymer is expressed in arbitrary units here. There is no specific need to think about a perfect unit, but nevertheless the cost in Indian rupees for an acrylic polymer or polycarboxylic ether based superplasticizer works out to about 120 to 150 rupees per kilogram. Okay. That is typically the cost of a PCE based chemical. So, let us say it is about okay. So, compared to this, melamine will be about 80%, melamine formaldehyde that is will be about 80% of the cost of your acrylic copolymer. Okay. Naphthalene will be about 40% of that cost, whereas your modified lignosulfonate will be only about 20% of that cost. But what you need to remember is what is the concentration first of all of the solution that you actually get in the market. So, typically acrylic copolymers or PCEs are available at 30% solids content. What do you mean by that? 30% of active solids dissolved in water, okay, whereas all the other plasticizers are available typically in around 40% solid concentrations. What is not given here is the effectiveness. So, let us put another column and mark it as effectiveness. So, I talked about the fact that superplasticizers based on graft chain copolymers like acrylic polymer or PCE are much more effective as compared to naphthalene formaldehydes or lignosulfonates, right. So, let us say we need 1% by weight of cement of the PCE based admixture. Let us say we need 1% by weight of cement. So, I will just arbitrarily put this effectiveness as 1. Let us say to get a 100 millimeter slump in a concrete which has 400 kilograms of cement, I need about 1% by weight of cement of the acrylic copolymer to get that workability. Okay. Now, for melamine, I will probably need close to about 1.3%, okay, 1.3% by weight. Melamine, naphthalene probably even more, maybe about 1.5% by weight of cement to actually obtain the same degree of workability as I obtain with 1% of polycarboxylic ether. Okay. And modified lignosulfonate, I will probably need 2% to get the same extent of workability as I get with the acrylic copolymer. So, now remember that you are working at already a lower solids concentration of the PCE. Okay. So, convert that 1% to the actual amount of solid content that is actually required. We are talking about 0.3% of the solid, right. Here it is about 0.52% of the solid, here it is about 0.6% and here it is 0.8% of the solid superplasticizer. That means the effective solid molecules of the superplasticizer that are required to produce the same degree of workability in the concrete. Okay. Everybody understood what I have worked out here, right. I am working out how much solid superplasticizer dosage I require to produce a given slump in a concrete which has approximately about 400 kilograms of cement per cubic meter. Okay. So, what I see is I need a dosage of about 0.3 from acrylic copolymer, 0.52% from melamine, 0.6% from naphthalene and about 0.8% from the modified lignosulfonate. Now, without going into this, this column here, if you translate this into the cost, can we look at the cost there? 0.3 multiplied by 100, right, cost of the dry polymer is 100. So, some random units, we are not really talking about cost in rupees or dollars or whatever, we are talking about cost in some random unit. So, 0.3 multiplied by 100 is 30, 0.52 multiplied by 80 is about 42, okay. 0.6 multiplied by 40 is about 24, right, and 0.8 multiplied by 20 is about 16. So, that is the cost in terms of the effectiveness, okay. In terms of the effectiveness, that would be the cost that I am looking at. Now, of course, I am having difficulty believing this, but what I have probably done is underestimated the amount of modified lignosulfonate required to actually get the same effectiveness. If you use 2% of modified lignosulfonate, you will definitely get this effectiveness. The only problem is you will also get significant amount of retardation. So, your concrete properties may not be to the level that you desire. So, what we need to look at is a comparison of your PCE and SNF. So, if you are able to assume that you are getting sufficient workability with 1.5% of the SNF, or which results in 0.6% of the solid SNF, then what you are ending up with is not much of a difference in the actual cost in the concrete, whether you use a PCE or a SNF based superplasticizer. Now, in the modern day concretes, what people are still trying to prefer is the use of sulfonated naphthalene formaldehyde, because the initial cost is only about 40% of the acrylic copolymers or the PCEs. But if you really compare the actual cost in concrete, what is the percentage difference there? So, 6 rupees out of 24. So, it is only about 25% difference. There is only about 25% difference in the cost. You may actually get better slump retention with the PCE. With 25%, is it worthwhile to pay for the extra slump retention that you get? Maybe yes, definitely. And later I will talk about the range of water cement ratios over which these admixtures are actually effective. What you will see is when your water cement ratio starts dipping to below 0.4, the effectiveness of the SNF sharply declines. SNF needs about 0.4 water cement ratio or more to be effective in concrete. So, if you are looking at less than 0.4, the effectiveness of the SNF starts coming down significantly. So, at that stage maybe the difference may not be that large anyway, it will still come down. The 6 rupees will further come down to probably 1 rupee or 2 rupees at the max. So, that way what I am trying to say is the more stringent the mixture design gets, the more economically feasible will be the use of specialized additives like the polycarboxylic ethers or acrylic copolymers. Okay. If you are dealing with day to day concrete construction, 25-30 megapascal grade concretes, in those cases your modified lignosulfonates or maybe just the SNF would be more than enough to really achieve the kind of properties that you want. Okay. But when you deal with concretes of grades M40, M50 and above, you are dealing with water cement ratios that are routinely below 0.4, and in that scale the economy of using the SNF may be quite similar to the economy of using a PCE based superplasticizer, and the effectiveness of the PCE would be better. Okay. So, this cost analysis is important because it gives you a handle as to how you can approach mixed design for large infrastructure projects. Again, initial cost is only going to get you to an erroneous decision. For example, if I just go with the initial cost, I will probably end up with much better cost analysis with the modified lignosulfonate. In terms of effectiveness, I will probably not get the same extent of performance that I want from the concrete. Okay. Now, very often we deal with situations on the field where things do not go as planned, especially when in the age that we have been using extensively different types of chemical admixtures in concrete, the compatibility problems have been on the rise. Now, compatibility here refers to the performance characteristic expected from a combination of cement and superplasticizer or cementitious material and superplasticizer. Incompatibility may result in one or more of these kinds of performance indications. You may have a poor slump retention with the concrete, you may have retardation, excessive retardation. In some cases actually I have got reports from sites which indicates that concrete has not set for nearly 7 days or 14 days in some cases. Okay, so poor slump retention, retardation, bleeding segregation and low early strengths, these are some of the problems that we expect to happen when we do not choose our mix design properly, especially if we do not have the right combinations of cement and superplasticizer. Okay. And in general, as I have been talking before, the kind of polymers which have these long side chains are known to have fewer compatibility problems as compared to the ones which work with electrostatic repulsion. Okay. So, now if you really want to get into an in-depth understanding of what constitutes compatibility, what are the factors that affect compatibility, this will take us a whole lot of time to actually do this, because if you really look at what people have done in literature trying to look at different parameters as to how they affect the compatibility, there is a whole lot of things that can be looked at. One is the type of cement and the composition of the cement. So, of course, you know that cement is composed of different compound compositions. Cement is also having several other additives, for example, gypsum. You have alkalis which are present as impurities in the halite and belite itself. You may have free calcium oxide that is present in the cement, and of course, you may have other minor phases which may or may not have an effect on the compatibility issues. But what you know very well is that the type of sulphate can make a major difference in the kind of hydration processes that happen in the early ages, right. We discussed this earlier, that if you have anhydrite or hemihydrate or dihydrate, you can get completely different rates of solubility, and that may cause a very different performance in the initial stages, right. On the other hand, you have the superplasticizer molecule itself. We talked a little bit about how the presence of low molecular weight components can entrain air in the system, the presence of sugars can actually lead to retardation and so on and so forth, and the fact that when you have high molecular weight components which are present in the superplasticizer, the adsorption is much better, and that leads to a much higher workability in the initial stages. Now, all these effects will also, as to how the interaction with the cement happens, will affect the early age performance of the concrete. And of course, in detail what is presented at the bottom is the kind of gypsum that you have in your system, that is your either gypsum or hemihydrate or anhydrite or natural anhydrite. So, you can have different kinds of calcium sulfates which will have different effects at the rate at which your reaction proceeds further, at the rate at which your cement interacts with the superplasticizer also. We will look at that in just a minute. So, we will primarily look at 4 major issues. What is the influence of the C3A on the compatibility, the influence of C3A to sulphate ratio, the alkali content, and also the fineness of the cement. Now, one thing you can say right now is what is going to be the effect of the fineness of the cement on compatibility or on the action of the superplasticizer. Can anybody tell me what will be the effect? If you choose a finer cement, what will happen? There is a greater surface area, so there will be more adsorption of the superplasticizer molecule. Now, please remember, this adsorption has to happen in stages. First, the adsorption should be on the unhydrated cement grains, but soon these cement grains start hydrating and producing the early phases of hydration like CSH and ettringite. So, you must have some superplasticizer still left in solution to further adsorb on these particles to still keep them in suspension, because we need to extend the workability as long as possible. So, the finer the cement, the faster will be the rate of adsorption of the superplasticizer, and probably that may lead to a lower effectiveness of the superplasticizer. In terms of maintaining the slump, your SP may not be as effective as before. Okay? But anyway, we will revisit that towards the later part of this chapter. First, let us look at C3A itself. Now, again the process of grinding of cement produces particles that get charged, and C3A generally ends up with a positive charge. So, without a doubt, the positively charged C3A will start attracting the negatively charged superplasticizer molecules. We saw earlier the structure of the superplasticizer. There is a charge imbalance that leads to the negative charge being imparted to the cement particles after the superplasticizer adsorbed on the cement particles, right. So, here there will be a preferential adsorption of the superplasticizer molecules on the C3A grains. Why? Because of the positive charge of C3A. There is also a lesser positive charge or almost neutral charge on the other grains, which will again lead to more adsorption by the chemical admixture, but you may lose most of it to the C3A because of the affinity to the sulfonate molecules, especially with SNF. Please remember, we are having the sulfonate contributed by the SNF also. As a result of that, there will be a competition between gypsum and the superplasticizer molecule for the sites on which you have more C3A content available, right. So, because of this, what will happen is part of your superplasticizer may get ineffective and block the C3A site. So, what will this do? You can lead to a retardation of the reaction of C3A, because more superplasticizer is getting adsorbed on the C3A molecules. So, the effectiveness of the superplasticizer is coming down. That means the initial workability may also come down, or retention of workability may be affected, but at the same time the setting of the C3A may also get delayed. Now, this is a unique problem. You generally expect that when the slump is not retained for a long time, the setting should happen fast, but here it is the opposite which is happening. Neither is the slump getting retained nor is setting happening fast, because your C3A molecules are getting adsorbed by the, or your superplasticizer molecules are getting adsorbed on the C3A particles. Okay. So, you get loss in slump and you get delayed setting also. Again, why delayed setting? Because your C3A needs to react with the gypsum to produce the ettringite that leads to the initial stiffening and setting of the cement pastes. Now, instead of that, if it is combining with the superplasticizer sulfonate, then it is not really going to be leading to the right kind of reactions that lead to setting. Okay. So, loss in slump and delayed setting together can really affect the performance of concrete on the job site. Okay. Generally, for low water cement ratio mixes, the loss in slump is accompanied by a faster setting, but here it is the opposite. Here you have loss in slump and delayed setting. That generally happens when you have combination of SNF superplasticizer with cementitious materials having high C3A contents. Okay. And the other effect that SNF can have is that it can inhibit the nucleation of gypsum. For example, if your sulfates are available in the form of anhydrite or hemihydrate, please remember that when they come into contact with water, they will first transform to gypsum, right. You have CaSO4 half H2O plus water, that is 3/2 H2O, will give you gypsum, right, CaSO4 2 H2O. So, that initial combination of the anhydrite or hemihydrate with water leads to a unique condition in your concrete. Can anybody tell me what condition that is? In the early stages, when you add water to the concrete, because of the presence of hemihydrate or anhydrite inside the cement, it leads to a reaction with water to create the formation of gypsum, which leads to some stiffening, and that is called false set. Yeah, that is called false set. Now, interestingly, when SNF is present in the system, it can inhibit the nucleation of gypsum. So, it can actually lower the possibility of false set. Now, how do you overcome false set anyway? What happens when this gypsum forms? You get a false set. How do you overcome that? Obviously, it is a false set, so it can be overcome. Not by adding water, by further mixing. You continue mixing, that overcomes the false set. Okay? So, false set is not really a problem, you can just overcome it by continuing to mix. So, what is my SNF doing? It is attracted to the C3A molecules or C3A particles. SNF is losing effectiveness because it goes and preferentially adsorbs on the C3A. It causes a loss in slump. It causes retardation because C3A is no longer available to interact with gypsum. Now, what I can do in this kind of a condition is that I can add my SNF a little bit late to the system. What does that mean? First I add the water to the cement. What will that end up doing? It will promote the interaction between sulfate and C3A first, right. It will promote the interaction between sulfate and C3A first, and then I add the SNF, and that will lead to a improved dispersion of not just the unhydrated grains, but also the initial hydrates that are actually forming in the system. Okay, so, this way my C3A is first already combined to some extent with the sulfate, and my SNF is not going to compete with the sulfate anymore for C3A sites. Okay, so, delayed addition is quite a good, very effective strategy to work with as far as SNF is concerned. With PCE, delayed addition may or may not do anything, because PCE does not have this issue of preferential adsorption on the C3A. Now, interestingly, what we have not looked at in the cement chemistry earlier, we will again try to cover that here in terms of the interaction between the C3A and the gypsum. The relative amounts and the reactivity of the C3A phase and gypsum that are present in the system can govern to a large extent what happens in the initial stages, and especially when you have a superplasticizer into the system, you may actually create different conditions of incompatibility that may exist in the system. So, let us look at what happens when you have different types of C3A and gypsum in the system. So, again this is something which is present in your textbook, you can read this in more detail. What I am trying to present here is the same scenario which happens in normal concrete without any superplasticizer. Let us see how that is affected when a superplasticizer is added. So, for all practical discussions, I will be restricting my discussion to sulfonated naphthalene formaldehyde, not PCE, because what we know from practice, at least in the last 20 years or so, is that whatever problems we have with SNF, we typically do not have with PCE. Okay. But later I will talk about some issues we may have with PCE also. But for now, all these discussions will assume that the type of superplasticizer I am considering is SNF. Okay. So, now let us look at a system without a superplasticizer first. If I have different reactivity of C3A and different availability of setting sulfate ions, I may actually get different setting times in my system. So, first let us look at a case when the C3A has a low reactivity, okay, and sulfate ions are not available fast enough in solution. So, what does that mean? What type of sulfate do I have in my system if my sulfates are available very slowly? Anhydrite or hemihydrate? No, those are the ones that are rapidly dissolving. So, if I have gypsum in my system, if I have mostly dihydrate or gypsum in my system, my sulfate ion will be available slowly. My reactivity of C3A is also low, and that will lead to a normal setting which happens in about 2 to 4 hours. Okay, that is a condition which we can live with, because in this case when I put in my superplasticizer, what will happen? If I have an SNF superplasticizer coming in, what is going to happen in this case? I may cause retardation. Why? Because this SNF is now going to be attracted to the C3A, my sulfate is available very slowly, right. So, my interaction of the C3A with sulfate may not happen immediately. In the meantime, my SNF may start going and getting attracted to the C3A particle, and lose the effectiveness, which may result in loss of slump, right, and retardation because C3A is getting blocked and my setting time may be extended to 6 to 8 hours in this case.
So why will there be a slump loss in this case?
Now again SNF, because C3A is not easily reacting with the sulfate, right, my SNF again preferentially adsorbs on the C3A, it may result in slump loss. So a possibility could be slump loss, so let us call it S, and retardation. Okay. Now what about the second scenario? I have a high reactivity of C3A and sulfate ion is available very fast. That means I have sources like anhydrite or hemihydrate also present, which can release sulfate very fast. And in the absence of a superplasticizer, I will probably get a normal set within 1 or 2 hours because I have very quick reaction between the C3A and the sulfate. So what will happen in this case when I add the SNF? Do I expect slump loss to happen? Probably not. Even in this case there will be affinity of the SNF to the C3A, but my sulfate is already very rapidly dissolving, right. So I may not lose my effectiveness by losing my SNF to the C3A. Okay. So I may not have slump loss, I may not have slump loss and I may not have retardation when reactivity of C3A is high and availability of sulfate is also high. So that may be a desirable circumstance to have, except the fact that it will result in a fairly quick set between 1 and 2 hours. I am talking about quick initial set, right. Now that gives you much lesser time for playing around with your concrete in terms of workability, open time and so on and so forth. So that is something you need to keep in your mind. So for example, if you are looking at ready mix applications, this may be a useful combination to use if your travel times are less. Okay. Now in the third case, when the reactivity of C3A is high and sulfate is not becoming available fast enough, in a normal condition this will lead to a quick set. Why do I call it a quick set? You may have some formation of calcium aluminate hydrate because of reaction of C3A with water. Okay. Some reaction of sulfate with C3A may happen in the early stages. Now in this condition you need to be obviously extremely careful when you add the SNF. What will happen here? When you add the SNF, your slump loss will be rapid. You will have rapid slump loss and retardation, well, you may actually bring the setting time to a normal time from a quick set, right. The retardation may be sufficient to bring your setting time to normal. So normal set probably. You will get a rapid slump loss and probably your setting time will come to normal because of the effective retardation that happens with the SNF. In this case there is not much to discuss obviously, because if reactivity of C3A is high and there is no sulfate in the system, that will lead to flash setting that happens because of the formation of calcium aluminate hydrate. Now there of course it is a system that does not exist, so we are not really going to talk about that. What about this condition when you have a low reactivity of C3A and a high availability of sulfate ion? That means you have a lot of anhydrite and hemihydrate present in the system. So as we discussed earlier, this will lead to the false set condition, which happens within 10 minutes, but this set is getting broken down, right. By further agitation of the mix, you will break down the false set. But what will happen in this case when I add an SNF? If I add SNF to this system, go back to this previous slide here, where we talked about the fact that SNF inhibits the nucleation of gypsum, right. So in the presence of SNF, there will be no false set. What about your slump loss? Slump loss may not happen, okay. Maybe no slump loss. What about your retardation? No retardation because sulfate is available quite rapidly. It can interact with the aluminate even though the aluminate is not as reactive. So no retardation. So what is the critical situation for us to deal with in this all these 5 cases? Of course the fourth case is not really true in regular cement. So we will have to deal with the first 3 cases or the last one. So which is the most critical case for us? The first one as well as the third one, right. The first and the third, where we have either a low or a high reactivity of C3A and mostly a low availability of the sulfate ion. So what we have to ensure is in our cement we end up having a combination of sulfates which is able to give me a very high rate of availability in the beginning itself, So, in both these cases sulphate ion availability is low in the beginning. So, whenever I have sulphates available early enough in the system from the gypsum type that has been added to the cement, I will be able to overcome this problem to some extent. Okay. And with the help of if my reactivity of the C3A is low, right, that again will lead to a process of retardation. So, what I need to choose is, so what should my cement have in order to be compatible in an SNF kind of system? I should have high reactivity of C3A and mixed forms of sulphate. Okay, so that there is a lot of availability of sulphate from the very beginning in the system. Okay. So, if you can fine tune your cement to produce something which has a reactive C3A, right, but at the same time you also need to be careful that the high reactivity of C3A will obviously cause a much faster reaction to happen. Okay. And you also have to be worried about the fact that this high reactivity C3A might lead to greater adsorption of the superplasticizer in case there is not sufficient sulphate available in the system. So, you have to use it together, the high reactivity C3A as well as the higher availability of the sulphate ion in solution, and that will lead to a situation where incompatibility may be avoided to some extent. Even in that case, your grinding of the cement, all that also still will have some effect in altering the compatibility of the system, but for the most part use of a high reactivity C3A and a mixed sulphate availability in your system in terms of anhydrite and hemihydrate contributing sulphate rapidly and gypsum contributing sulphate in the later stages, that will lead to an effective performance in your cementitious system. Now, alkalis are something that generally lead to a poorer rheology. Okay. Now, modern cements have higher alkali contents. Okay. Now, that is an aside, but even with lower alkali cements the durability is not affected in terms of pH. Okay. Higher alkali contents basically lead to a higher reactivity. Especially when you talk about C3S phases, the higher alkali content can lead to a much greater reactivity, because again you are talking about alkali sulfates mostly, right. So, alkali sulfates very quickly come into solution. So, sulphate from alkalis are also available in the solution. So, if you have higher amount of alkalis present in your system, generally your reactivity of your cementitious phases, particularly your C3S and C3A phases, is much higher, and we want always a very high early strength from your cement. So, because of that higher reactivity is generally preferred. So, most cements would tend to have high alkali contents. In India, we have alkali contents of about 0.6 to 0.8% of sodium oxide equivalent. If you go to the US, most cements would have about 1 to 1.2% of alkali content. Please remember, alkali contents in cement are expressed in terms of sodium oxide equivalent. So, alkali oxides present in cement are sodium oxide and potassium oxide. You convert that to an equivalent sodium oxide percentage. Okay, that is how you will be seeing the proportion represented on a cement mill sheet. Okay. So, in the US you will routinely deal with alkali contents which are of the order of 1 to 1.2%. Okay. So, in higher alkali cements you have to really ensure that you put in more superplasticizer to get sufficient amount of workability in the system, because higher alkali cements will have poorer rheology, poorer flow behavior. Okay. So, in general, what are the types of materials that you need to work with for good compatibility? If you look at cement, we already talked about this fact that if you have too much fineness, it tends to increase the rate of adsorption. So, you want the cement to be not ground too fine. Now, what does that mean, not ground too fine? In terms of fineness, in terms of square meters per kilogram, what would you say is an ideal fineness for the cement? So, we get an entire range, right. So, we do not know this. I just wanted to bring to your notice that this is something which you can't really govern, because the fineness will be dictated by the kind of strength gain properties that you desire from the cement, right, depending upon what is the expected level of performance in terms of strength. For example, I showed you those EN cements, right, which have 2 day strength requirement. In those cases you have to grind cement fine, you have no other way out of that. Okay. So, when you have the chance to grind cement finer or coarser, not grinding too fine may help in reducing the compatibility problems. Okay. Or if you are having a compatibility problem with the cement, opting for a lower fineness may actually help get rid of some of that compatibility problem. Okay. What about C3A? Generally it is seen that C3A in cubic form, which presents a high reactivity as opposed to the orthorhombic form, can lead to a much better compatibility in a cementitious medium. Lower alkali content is always better, and gypsum polymorph of high solubility, of course, or a mixed gypsum polymorph, or rather mixed combination of gypsum, for example mixed combination of anhydrite, hemihydrate and dihydrate in the system. SNF, you need to avoid low molecular weight materials because that leads to air entrainment, and sometimes the sugars present in ligno or SNF can also cause retardation. And we also saw earlier that in the structure of the SNF, if your sulfonate is present in a particular location, it enhances the effectiveness of the SNF. In beta position, sulfonate seems to enhance the effectiveness. And PCE, usually there is not much compatibility in terms of compatibility issues, you do not really see much in a cementitious system. However, there may be some reports of slump loss even in cases where PCE admixtures are used. That is because they are generally being used in concretes which have lower water to cement ratios. So, in those systems there are possibilities of compatibility issues. We will talk again about that later. So, in quality control, we do not really have a choice about what is the composition and what is the nature of the cement in terms of the type of C3A, the form of C3A and so on and so forth, right. And we also can't control the molecular weight of the superplasticizer, the fact that your sulfonate is in the beta position or whatever. All that is governed by the manufacturer of the cement, manufacturer of the construction chemical. In most cases, as a quality control specialist on the job site, you will have to deal with whatever you are getting. But before you set out to make your concrete, there are some simple test methods that can be done to evaluate the compatibility between cement and superplasticizer. So, let us take a look at some of these. One simple test is the Marsh Cone test. Now, this test itself is derived from something that has been used for a long time for grouts. Okay. So, as the name implies, it is just a cone. As you can see, it is a cone, it is a funnel essentially, it is a cone which has an orifice at the bottom, and this orifice, the size of this orifice is typically 8 millimeter, okay, or sometimes even when mortars are used instead of paste, when you use mortar you can have a size of about 12 millimeters opening at the bottom. So, what is essentially done here is that you prepare your cementitious paste with the required dosage of superplasticizer, okay, with different dosages of superplasticizer, and you prepare about 1 liter of paste that can be poured into this funnel. You close the bottom of this funnel with the tip of your finger, and after you have poured the required volume of paste into this funnel, you then remove the tip of your finger, open the orifice and allow the cement paste to flow out of the cone, right. And what you simply measure is the time taken for this paste to flow out. What we do is typically take the time taken for about 500 milliliters of the paste to flow. So, you put about 1 liter paste inside and you measure the time for 500 ml of the paste to flow out. And when you plot this flow time against the superplasticizer dosage, so you prepare cement paste mixes with varying superplasticizer dosages, increasing from 0 to the maximum permitted value in the system. So, what you will see is when you plot the flow time against SP dosage, as you have more and more SP available, you will have a reduction in your flow time. But what you will see is beyond a certain point, there is no significant decrease in flow time with an addition of extra superplasticizer. Okay. If you were to compare this to a law in economics, it would be to the law of diminishing marginal returns. Okay. So, you put in more and more superplasticizer, beyond a given point you see that there is not much significant reduction in the flow time. Now, what do you think is happening physically in that? So, what is causing the flowability in the system? The adsorption of the SP molecule on the cementitious grains and the resultant repulsion or steric repulsion or whatever it may be, right. So, what do you think is happening at that dosage beyond which extra SP is not really doing much in your system? So, there is no extra surface left. So, whatever extra SP that you add is simply going into the water, right. It is not really doing anything for further plasticizing the cement grains. So, effectiveness of the SP beyond this dosage is not significant. As a result, the flow time does not get enhanced significantly beyond that dosage. So, that dosage is called either optimum dosage or saturation dosage. Okay. Now, this is a test on paste. Okay. Now, what if I take this to concrete? If I check this dosage, optimum dosage that I have determined from this Marsh Cone test, and I use the same dosage in concrete, what do you expect will happen if I use the same dosage in concrete? What are the other components apart from the paste in concrete? I have aggregate. So, if I have aggregate also, what is going to happen? Aggregates also are porous and they also have surface charge. They may also adsorb, or superplasticizer may also start getting adsorbed on the aggregate particles, right. So, some effectiveness of the SP will get lost. In other words, in concrete you will definitely need a dosage greater than optimum dosage to result in any degree of flowability that you may want. Okay. Now, I am not saying that at optimum dosage in concrete you may not get any workability at all, you may get some level of workability, but you may want to plan as to how much additional SP that you need to add to concrete to give you the correct level of workability in the concrete. Okay. So, the optimum dosage in paste may or may not translate into the required workability in concrete, because in some cases in concrete you want a workability of 200 mm slump, in other cases you may want a slump flow of 600 millimeters. So, all from the same paste that you are studying with Marsh Cone test. So, the optimum dosage may or may not translate into the kind of characteristics that you want in the concrete. So, generally what you do is you use it in combination with another test called mini slump test. That is what I will come to in the next slide, but before that, how do we use this Marsh Cone for compatibility studies? So, this is one of the methods that is suggested by one of the leading researchers of our times, Pierre-Claude Aitein, and he has worked with lot of superplasticized systems, and based on the work done by researchers at his university in Sherbrooke in Canada, they came up with this sort of a scheme that for a compatible combination of cement and superplasticizer, if you do the test at time t equal to 0 and the same test is repeated with the same paste after 60 minutes, right. If you repeat the same test after 60 minutes, the curves of the flow time versus percentage of superplasticizer will coincide beyond the optimum dosage. Okay. So, what you are trying to say is, after 60 minutes if I perform the test on the same paste, obviously I expect that my flow time is going to get higher, right, because my slump is getting lost, right. At a given superplasticizer dosage my flow time is going to increase, correct. But at SP dosage which is optimal, I have sufficient superplasticizer in there that even after 60 minutes my paste has the same flow time as it had initially. So, that is one of the definitions that Aitein et al. Have come up with for a compatible combination of cement and superplasticizer. In the same token, an incompatible combination means that this curve entirely shifts after 60 minutes to the top. I am sorry that there is not much distinction between the curves here, this is at 0 and that is at 60 minutes. That means this is the initial flow curve and that is a 60-minute flow curve. After 60 minutes you test the same paste after it has been remaining in your mixer, you mix it again after 60 minutes and then test the flowability, and that is the kind of flow that you will get after 60 minutes. So, for an incompatible combination the curves completely get separated. So, for any dosage of SP the flow time gets increased even after optimum dosage. Okay, fine. So, we will think about the physical significance of this and apply this to some real experiments that we have done in the lab and see whether this actually holds good in terms of assessment of compatibility in the next class tomorrow. Thank you.